Okay, this is Dr. Brown. This is a video that'll be relatively short on continuity. It's about a topic you probably already know quite a bit about. I'm just going to remind you a few things and give you a more precise definition of continuity and give some examples. First, we have a graph here of a continuous function. Imagine that you were plotting the path of an object that is falling from t equals 0, and you plotted 4 points given q1, q2, q3, and q4, and you did a plot from 0 to 10 seconds. Obviously, this ball or object will occupy every position between 0 and 500 feet, even though you may have only plotted 4 points. You know that the ball is somewhere between 0 and 500 during the first 10 seconds, and all the points are connected to one another. In other words, there are an infinite number of points on this graph. And so we say this is a continuous or connected function. Now, this function is obviously not a continuous function. It's just indicating various things. You can see that between 0 and 1 that the function is continuous. Then it has a hole in it, and the graph jumps up to +1, and then is continuous between 1 up until 2. Then there's another hole in it at the point 2 and 1. In other words, that point does not exist, but the functional value of 2 is equal to 2, and the functional value of 1 is equal to 1. The function is then continuous, and continues to be continuous up until x equals 4, and then takes another jump. So this is a very discontinuous function, although it does have a lot of points that are continuous. Now we have the concept of two-sided continuity and continuity from the right, continuity from the left. For instance, if you have a point C that is internal on the domain of the function from A to B, and coming in from the right, the function is continuous, or coming in from the left, the function is continuous, and then coming in from the right, the function is continuous. It's said to be a two-sided continuous function. Obviously, if you have endpoints to the left where the function begins at x equal a and where the function ends at x equal b, you can have what we call continuity from the left on the right hand side, and then continuity coming in from the right on the left hand side. And obviously the function is not defined outside the interval from A to B. Now this is a formal definition of continuity. For an interior point, a function y equal f of x is continuous at the interior point C of its domain if the limit of f of x as x approaches C equal f of C. Now for an endpoint, a function y equal f of x is continuous at a left endpoint, or is continuous at a right endpoint if coming in from the right the limit of f of x as x approaches a from the right equals f of a, or if coming in from the left, the limit of f of x as x approaches b from the left is equal to f of b, respectively. Now I'm just going to show you some examples of continuous functions. This is a function y equal the square root of 4 minus x squared, and it's a semicircle. You probably remember from college algebra that the equation of a circle with radius of 2 would be equal to x squared plus y squared equal 4. And of course the radius is equal to the square root of 4, which is 2. Now we can solve for y, and y is equal to plus or minus the square root of 4 minus x squared. And if we just take the positive result, we have a function that is a semicircle, the top part of a circle. Here is a what I call a step function that's used quite a lot of time in all kinds of engineering and timing functions. The function is discontinuous at x equals 0. Obviously it's equal to 0 on the left, and then as x approaches 0, it jumps to plus 1 as x equals 1, and as x equals 0. So it has what we call a jump discontinuity at the origin. A test for continuity: a function f of x is continuous at a point x equals c if and only if it meets the following 3 conditions. First of all, f of c must exist. In other words, there is no hole at x equals c, and the limit of f of x as x approaches c exists, and that limit that exists must equal f of c. So this says the limit equals the functional value, which is pretty reasonable. This function is one you may have seen back in college algebra. This is called the greatest integer function. For instance, the greatest integer in 2.1 is equal to 2. That's why at 2.1 the functional value is equal to 2, and the function takes a jump and has a discontinuity as at every integer value it will jump by plus 1. Now here are some examples of a function. First of all, the first function is y equal f of x. It's a straight line that goes through 0 and 1, and it's continuous at x equals 0. But each of the next functions from b through f are all discontinuous at x equals 0. The b example is discontinuous just because you put a hole there and said that the point 0 and 1 is not on the graph. In the c example, there's a hole at 0 and 1, but the functional value f of 0 is defined to be 2. Might even sound a little arbitrary, But anyway, it's not continuous at x equals 0. Then next, the step function that we previously looked at is not continuous at x equals 0. And then the rational function 1 over x squared is not continuous at x equals 0 because it has a vertical asymptote. It's continuous everywhere else, a very nice continuous function, except at x equals 0. And then finally, the function y equals sine of 1 over x, which we had looked at before, is not continuous at x equals 0 because at as x gets closer and closer to 0, the value of sine of 1 over x oscillates between plus and minus 1 and never settles down. Another function that we've looked at, the reciprocal function y equal 1 over x, is continuous everywhere except x equals 0, where it has a vertical asymptote. Now, there is a pretty obvious or intuitive property of continuous functions, that if you have two functions f and g that are both continuous at x equals c, then if you add the two functions, that function will still be continuous. If you take the difference, it'll still be continuous. If you take the product, it'll still be continuous. If you multiply one function by the constant k, that new function will be continuous. If you divide one function by the other, the function f over g will be continuous unless g at c is equal to 0. Then, of course, it will have an asymptote there. Also, if you take any continuous function and take the r over s power of that function, the resulting function will still be continuous. In other words, if you take a continuous function like sine of x and took it to the 2/3 power, that function is still continuous. And then we have a function here, x sine of x divided by x squared plus 2 in parentheses. If you graph this function, you'll get quite an interesting plot, which, by the way, I have seen during all my career, because this can show what the power in a transmission from a radio station could be, or a transmission from a satellite earth station could be, when it's sending all kinds of data. But look, it is continuous all over its domain. And then finally, the last thing we're going to talk about is called the intermediate value theorem for continuous functions. And this is one that I call is sort of common sense. If a function is continuous from A to B, and the value of the function at x equal a is f of a, and the value of the function at b is equal to f of b, you conclude that the function on the interval, closed interval between a and b, takes on every value between f of a and f of b. It's pretty obvious that if this function has to be continuous, it's got to take on all the values in between. And one practical thing that occurs very often we have to find zeros of functions. And if you knew that a function was below the x-axis at a certain point A, and at another point B it's above the x-axis, and you know it's continuous, you know that it has to cross the x-axis at least at one point. Now, if you take, for example, a function f of x equal x cubed minus x minus 1, and you plotted it, you would get a plot like this. In fact, you could put it in your calculator. If you see that the value of the function is below 0 at one point and above 0 at another point, you know that somewhere between here and here that there has to be a 0. And you folks should know how to do that on your graphing calculator. And if you, why don't you practice it, and I'll show you or remind you how to do it in class on Monday. You can find that the 0 is actually 1.3247, and that's it for continuity.